So yesterday or last day, we talked about some chemical or petroleum processes like cracking. We did octane, we talked about octane number. That's not a process. But then we looked at alkylation and then isomerization. I think, yeah, I didn't finish isomerization, so I guess I'll kind of finish that, and then we'll move into platforming and then the next section. So this is kind of where I left off today, or yesterday. So isomerization helps or complements the catalytic reforming process to upgrade the octane number for a petrochemical or petroleum product. So, typically in refining process, it's not like you would use just cracking or just isomerization. You would use both. Isomerization is simple, it's cost effective, and it enhances octane very effectively compared to other processes. Another good factor or another good feature of isomerization is that the product has low contaminants, so low amounts of sulfur and benzene. So it's really good gasoline component. It's one of the better processes. So isomerization, hard to say, is definitely a process you would want to know. This type of isomerization you don't actually see in the lab as much as you would see it in large applications in refineries. So, not something that we would do at the college in the lab, but you might see out at, in a RAS gas refinery or, anywhere in the world where crude oil is refined. So basically what happens in this type of isomerization is a straight chain alkane is converted to branched isomers by heating it with platinum or acid catalysts, very much like cracking, right? It's kind of the same idea. We use some heat and we use a catalyst, but different from cracking, where in cracking the molecule just breaks. In isomerization, you get branched molecules. So some examples of this, and you don't need to know how to write these. So, don't stress out about trying to write these formulas or chemical equations, sorry. But an example of isomerization is to convert butane into isobutane or pentane into isopentane. So this is an example of pentane, and we could turn it into 2-methylbutane or 2,2-dimethylpropane. These are branched isomers of pentane. So again, it's different than cracking. Cracking would take a much larger chain and break that into smaller pieces. Isomerization doesn't break anything. It just rearranges the molecules. And very, very important, wink, wink, fuels that have more branching are favored by combustion engines because they have a higher octane rating. They're better fuel sources when they're branched. So one of the reasons why isomerization is so useful is because it instantly increases the octane number by adding branches. All right, cool. So this is our last type of process. It's called platforming. Platforming, so again, the list is I see there's a couple more people joining me today. We did cracking. We did alkylation. We did isomerization. And then we did what we will be doing right now, platforming. So these are the four. And the thing is in other college courses, you guys probably have learned about this. You've probably heard about cracking at least, or isomerization maybe. You don't need to like know these perfectly, but just know the differences between them. So cracking, taking a large carbon chain and breaking it into smaller ones. Alkylation, that's taking small groups and putting them together to making something that's slightly more larger. So adding a small alkyl chain to a carbon. Isomerization, it's similar in setup to cracking, but instead of breaking the molecule, we just rearrange it. So like that's really all you need to know here. These very simple, straightforward definitions. And the last one is platforming. Platforming is the reforming chemical process used to convert naphthas, that's carbon chains with the 5 or 6 carbons. It's used to convert naphthas into high octane liquids called reformates. These are premium blending stocks for high octane gasoline, very high octane rating. Okay, so we'll talk about this process now. I just got a message in the chat, which I'm going to read. Naim, yeah, this is in your course outline, and maybe something new for you guys. You might not have done it in any other courses. It's pretty interesting. So I'll kind of explain it in the next couple of slides. So why is it called platforming, right? Like when I think of a platform, I think of like a flat surface, a platform that you would stand on, like a stage. But the name platforming comes from the fact that they use, again, a platinum catalyst. We've seen a catalyst in a few of these. So the name is a portmanteau, if you're familiar with that term. That's a term in English where you put two words together. So they put the words platinum and reforming together, platforming. That's where the name comes from. And again, it's because it uses a platinum catalyst. So what is it? Well, okay, I mean, really, it's a conversion process. It takes naphthas. So naphthas are like 5 to 6 carbon chains into high octane liquids with a high octane rating that are really premium gasolines. So what the process is, or what the process does, is it converts low octane number linear hydrocarbons, which they call paraffins, but you don't need to worry about that, just linear hydrocarbons, into branched alkanes. Remember what I just said on the previous slide. Branches increase octane rating. And also cyclic naphthenes, which are then dehydrogenated to produce aromatic hydrocarbons. So cyclic naphthenes, these are, cyclopentene, cyclohexene, but then are dehydrogenated to produce aromatics. So platforming takes low octane linear hydrocarbons and turns it into branched alkanes or high octane aromatic hydrocarbons. In all cases, it's making high octane rating products. So it takes a linear hydrocarbon, turns it into a branched alkane or an aromatic. There are many chemical, like this is a very, very complex reaction. I don't have a picture or a schematic of the platforming situation like I did back here. I had a little schematic, but you can almost imagine it being similar to this. Very complex process, which is not part of the chemistry course. We only care about the chemistry. So the key is that all of these chemical reactions take place in the presence of a catalyst and lots of hydrogen. And the hydrogen helps the reactions. And I'm going to show you the reactions on the next two slides. So depending on where you are in the world, like what type of reforming you're looking at, the temperature range is about 500. right? 495 to 525, and very high pressures from 5 to 45 atmospheres. The 45 is extremely high pressure. You don't have to remember these numbers, guys, don't worry. The only thing I want you to remember from this section is, like, just in one sentence, tell me what the process is. Or if I showed you, like, if I showed you something like this image, which type of process would you think this image is? And I mean, this one's an easy one because we're forming isomers. These are isomers. So you would say isomerization. Cracking is another easy one. If I gave you a long carbon chain and showed you that it broke into smaller carbon chains, that's cracking. Platforming is a pretty easy one. Now, there's 4 major catalytic reforming reactions. Okay, so if I show you a cyclic hydrocarbon that turns into a benzene ring, that's platforming, right? We have a high octane benzene ring. Or I shouldn't be even saying benzene, should I? I should be saying aromatic. So, again, if I showed you this reaction where you're forming an aromatic, the only one of the 4 reactions or 4 processes that forms an aromatic is platforming. Platforming also can be used for isomerization, which we've already talked about. This is a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain, and it's being rearranged to a branched hydrocarbon. So this you could call platforming or isomerization. Like, the platforming process is a high pressure reaction with a platinum catalyst, very similar to isomerization. So a product of platforming is also isomerization. It's kind of like a multi-talented chemical process. It can do many things. So we can make aromatics, we can make branched alkanes. Let's just make sure that this is an isomer over here. We have 8 carbons, so let's check this one. 1, 2, 3, 4, 5, 6, and then our 2 methyl groups, 8 carbons. That would be isomerization. Platforming can take a this is a really cool one. Platforming can also take an alkane, and through dehydrogenation, meaning removing these hydrogens, also turn it into an aromatic. Wink, 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 guys. If you see an aromatic, it's platforming. Okay, it's the only process of the 4, cracking, alkylation, isomerization, and platforming, sorry, the only one, I don't know what happened to my voice there, the only one that makes an aromatic is platforming. All right, and platforming finally can also, because it's high pressure, high temperature, and has a catalyst, platforming can also crack molecules. So platforming is kind of like the do everything. It can isomerize or create isomers. It can create or perform cracking, so break things into smaller molecules, and it can form benzene rings. One of the more powerful and interesting chemical processes. Platinum reforming, very cool. Remember, you do not have to write these, or you don't even have to memorize these formulas. Just know that if you are creating, if we're refining a petroleum product and we're creating aromatics, it is platforming. All right. So this brings me to one of the most important sections, and I won't do too much. I mean, it's only 10 to 1, but I'll get a little deep into this section here, and then we'll take a break for this Thursday. But this is actually a pretty important section, especially with this diagram I'm going to show you in a minute. The composition of petroleum and natural gas. Now, one thing that's really important to remember about compositions of petroleum, and I thought I might have had it. Yeah, okay, it's on the next slide. But just one thing to keep in mind about the composition of petroleum, and I will get into this on the next slide, it's not the same everywhere in the world. Like the crude oil or petroleum in even in like Saudi Arabia is not the same as the stuff you'd get here in Qatar. You know, certainly the stuff you would see in Canada, the tar we get in Canada, we typically get our oil from offshore, like in the ocean, or in the tar sands in northern Alberta, like northern central Canada, central west Canada. Anyways, they're all different. So the composition of petroleum can be really hard to define, but most crude oil would contain alkanes, cycloalkanes, aromatics, and other compounds that contain nitrogen, oxygen, sulfur. You could have trace amounts of metal in your crude oil, so iron and nickel and copper. And you could also have bacteria. Many oil reservoirs contain live, living bacteria. I'm glad to hear that, and I am that you're looking forward to it. This is a good section, or an interesting section. So again, crude oil it's so complex. Like the chemical makeup, chemical composition is incredibly complex. You can't just, say define a couple of chemicals and say that's it. There's hundreds of hydrocarbons in crude oil, from alkanes to aromatics, and then there's other things. So I'm going to kind of break down some of this composition for you. The other important thing that I've already mentioned this, but where the exact molecular composition of crude oil varies from formation to formation. So what I'm saying here is it's different all over the world. You really have to think about what petroleum is. Petroleum is a byproduct of, many, many, many years of decomposition of organic material. So depending on where you are, like we're obviously in the Middle East, the organic material here is different than, say, in the jungles of, South America, or in the north of Canada. So because like the living things, the plants and animals are different everywhere in the world, so is petroleum. This is a rough guide. You do not have to memorize this, but I would encourage you to know that petroleum is mostly carbon and hydrogen, okay? You don't have to memorize these numbers, but it's good to know, and it's very common sense to know that, all over the world, petroleum is different, but they do have one thing in common. Petroleum is mostly carbon, then followed by hydrogen. So carbon would be in the 80% range. Hydrogen would be, 10 to 15. Nitrogen, oxygen, sulfur, all less than 10%. One thing that's really interesting, this is, I'm sorry, I'm not going to put a star by that because you don't have to memorize this. But something that's interesting is look at sulfur. It can be like basically non-existent, or 0.05%. It can also be 6%, which is a lot. And again, this is where, the ranges all over the world kind of come into play. Everywhere in the world, it's mostly 80% carbon, 10% hydrogen, but the sulfur amount can range a fair bit depending on where you're getting the oil from. And like, I don't have any answers for this because an analytical chemist in Qatar would know the breakdown of the oil that's found in this region. But basically you would have to do research is what I'm saying. I can't tell you where in the world sulfur is higher. You'd kind of have to actually do the research, look it up, which I didn't do because it's not part of this course. Okay, so on this slide 44, I'm talking about elements. What about molecule generalizations? Like, what I mean is, if we group together molecules kind of by their similarities. So alkanes, for example, alkanes in the oil and gas industry, sometimes they call them paraffins. These would be on average 30%. Now, again, this is an average of these groups found in petroleum. It can range, depending on where you live in the world, from 15 to 60%. So again, there's no answers here. You do not have to memorize any of this. It's just, I'm just telling you that, wherever you live, the composition of petroleum can be different and it can range fairly highly. Naphthenes, like a naphthene, or nap means kind of like 5 to 6 carbons. So a naphthene, what I was trying to say is naphtha would represent 5, 6 hydrocarbons. Naphthenes would represent 5, 6 hydrocarbons with double bonds. So an example of a naphthene would be like cyclohexene. Okay, naphthenes on average are almost 50%. So in petroleum products all over the world, or not petroleum products, sorry, petroleum or crude oil all over the world, naphthenes you do get a fair amount of. They are also in the 30 to 60% range. Aromatics, if you took the average, would be around 15%. And asphaltics, these are, large hydrocarbons, very kind of viscous. That would be around 6%. Okay. And again, you don't have to memorize a single number there, but it's just interesting to know kind of the general composition of petroleum. So you have a mixture of alkanes, alkenes, or specifically cyclohexene would be an example of that, aromatics, and then asphaltics. Oops. So yeah, crude oil composed of a mix of hydrocarbons. So the products formed from fractional distillation is also a mix of these complex molecules. What I'm saying here is fractional distillation does not produce fractional distillation of crude oil product. So in the lab, I told you guys in the lab that the difference between fractional distillation and distillation is that fractional distillation helps you make a pure product. Well, because crude oil is so complex, and a lot of these hydrocarbons have very similar boiling points, and they're all mixed together, fractional distillation won't create a perfectly pure product. What we get are groups of products, as you can see here. Now, wink, 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 this is a very good slide to know. Basically, what you would need to know here is you don't need to memorize any really specific numbers, but what you should know are the order of the products that come out of a petroleum fractional distillation tower. These are called fractions. And in the past, I've had students I've given them this image, and then I've left these blank, and I've had like a fill in the blank question. I had a word list over here, and they'd have to kind of fill in the blanks. I'll show you this once, when we get closer to the final exam, I'll show you kind of a sample final, and we'll look at some practice problems. But one of the practice problems, or one of the questions I typically asked, was for the students to put these in order. Okay, so let's go through this. Let's talk about this. This is a really important image. Now, this isn't, again, this is an image. This is a generalization of a distillation tower. So this is kind of, in theory, in general, how they work. Wherever you go in the world, fractional distillation towers are different, but they all follow the same process. At the top of the tower, you have your lowest boiling point. These are the chemicals that boil off first. These would be 1 to 4 hydrocarbons, and these are gases. These would be your natural gases, methane and ethane particularly. Your naphthas are your 5 to 6 carbons. It can go up to 10. These are a little bit bigger than your, longer than the gases. These are typically liquids at room temperature. So naphthas contain 5 to 10 carbons. They have a little higher boiling point. You do not need to memorize the carbons or boiling point. But these would be gasoline products. So naphthas are your kind of liquid products. Then, again, look at the carbons. They're getting bigger and bigger and bigger and bigger and bigger. When you get past 10, you get kerosenes and gas oils. These are very similar. They're very much related. So they would be between 10 and 60 carbons. These are things like jet fuel, diesel, or even feedstock that you might crack down to make something later. So kerosenes and gas oils, they could be used like kerosene for home heaters, jet fuel, diesel fuel, or you could actually reprocess that by cracking to make naphthas or gases. Okay, as we're going down this fractional distillation column, you'll notice a few things. The carbons are getting bigger, the boiling points are getting bigger, but another thing that you might not think about here is they're getting more viscous. Do you guys remember that word? I don't even know how to spell viscous. Hold up. Well, apparently I did know how to spell it. I just typed it in on Google to make sure. So if you've never heard the word viscous, what does that mean? Viscous is, now, okay, I'll give you the fancy definition first. Viscosity is the definition of a chemical's resistance to flow. That's the fancy definition. The simple definition is viscous is thickness, how thick something is. Now, what do I mean by thick? Imagine you had two cups, two mugs, coffee mugs or something. And in one mug or cup, you put water, and in the other mug, you put honey. Which would pour out faster, right? So you take your two cups, you have a cup of honey, you have a cup of water, and you tip them over, which would pour out faster? Well, obviously the water. Water is less viscous than honey. Honey is thick. If you cook, you use the word thick a lot, right? You might thicken a curry or thicken a stew to make it more viscous. So as we go down this list, they're becoming thicker. We have gases, then we have gasoline, then we get things like jet fuel or diesel. They're still not that thick. But down here, you get lubricants, things like motor oil. Motor oil is very viscous. In the lubricants place here where it's bigger than 60, very high boiling point, it can also be used for cracking. Okay, under lubricants, you have fuel oils. These are 70 or more carbons. These could be like candles. Now, guys, candles are solid. So we've gotten to the point where we went from gases to liquids to solids. Okay, now this is at room temperature. Obviously, when we're heating this up, they would boil away. But at room temperature, we have gases, then we have the liquids, and then on the bottom here, we have solids. So fuel oils could be used for candle or oil for ships and power stations. This is very dirty burning oil. And then at the very, very bottom, we have asphalt. Asphalt would be a solid at room temperature. It's used for roofing, for making roads, asphalt roads. So there you go. Now again, I would definitely make sure you know that gas, okay, like you don't have to memorize any of this stuff on the right, but you should definitely know that gases are on the top, followed by naphthas. Naphthas is a word you should know. It refers to gasoline products or hydrocarbons between 5 and 10. You would get oils and lubricants in the middle, okay? You don't really need to know kind of how these guys separate. And then at the bottom, you would have fuel oils like candles, like very thick, solid chemicals. And make sure you know asphalt is on the bottom. So again, typically, guys, I would give this on a test or on the final exam, sorry, and I would leave these words out and you would have to fill them in. And I would give you a word list. You don't have to memorize the words, but I would say, okay, basically I'd take these words and move them over and say, put them in order. So gases are at the top, then naphthas, then you get your kerosene and gas oils, then your lubricants, then asphaltics on the bottom. Cool. Pretty interesting. Oh, one thing I'll mention too, actually, sorry, before I move on, I think I'm going to finish here today. Yeah, I think I'm going to finish after this because it is a good kind of place to finish. But before I finish, a petroleum distillation tower is different from the fractional distillation you guys saw in the lab. Why is it different? Or like, how is it different? This is actually, I find this interesting. Okay, so in the lab, the fractional distillation column, okay, well, actually, let's look at two things. Let's look at three things. Simple, fractional. In a simple distillation column, and I'm not an artist here, but you have your thermometer, you have your condensation tube. I guess your condensation tube is sloped. Let me do this a little different. So we got our thermometer, we got our condensation tube. That's my very rough drawing of a simple distillation. A fractional distillation, you have a much taller column. This is an easier one to draw. And you collect your product over here. So again, like the idea is I'm just trying to sketch the difference between simple and fractional. So simple, your chemical boils, turns into a gas and collected over here. In fractional distillation, your solution boils, it travels up a much longer column, turns into a gas, condenses, you collect it over here. In industrial, it is definitely fractional. But here's what's different about the industrial is you have your column, but instead of like one collection at the top, what an industrial fractional column does is it collects it at different points. So as the gas rises, the higher boiling points would be at the bottom. The gas boiling points, or the lowest boiling points, would be at the top. So an industrial distillation column is a little bit different than a lab, because in the lab, we have one collection. But see, in the lab, guys, when you guys do a distillation, you're purifying and getting one product. Industrial is so complicated and so complex, like crude oil is so complex, you're getting multiple, like, hundreds of different products here. Maybe not hundreds, but you're getting a lot of different products. Okay, so guys, last thing I'm going to mention, and this is good because it'll get us ready for class next week, is non-carbon compounds. Besides all of these carbon compounds, the fractions can have non-carbon compounds that contain nitrogen or sulfur or things like that. So I'm going to leave it here, but next week we're going to look at a couple of the compounds that can also be in your fractions, and then we'll get into maybe one of my other favorite chapter or sections, the thermal properties, section 5.1. We'll get into that next week. Okay, guys, so that's it for today. Have a great weekend. Oops, I just stopped sharing. Sorry about that. Have a great weekend. And if there's any questions, let me know. Other than that, like I said, have a fantastic weekend. Thanks, guys. Thanks, Saud. Thanks, Naim and Abdullah and Abdulaziz and Bashir. Not sure if I'm saying that right. And thank you, Abdullah. Thanks, everybody. Have a great weekend. Wear a mask, wash your hands.